Every year in the United States alone, an average of 1,000 people are fatally shocked in accidents involving 600 volts or less. A shock at as little as 30 volts can kill you if there's enough current involved. The electrical man here is to help demonstrate how current passes through the human body. For example, right now he's hooked up with one hand on the negative side of the circuit and the other hand on the positive side. The point is that electrical current will take the shortest possible path through your body. In this case, it's through the heart. That's what happens when your two hands are touching energized conductors source to source, or when one hand contacts a source and the other hand touches a grounded object. Now, let's try another example. Let's say only one hand is touching an energized conductor. Now watch this. What happens now is the current takes the shortest possible path to the ground. It goes up the arm, down through the body, and out through the nearest leg. In this case, the shock misses the heart. It's confined to only one side of the body. Now, this illustrates an important safety point. If you have to work near energized circuits, work with one hand as much as possible. Keep the other hand in your back pocket where it can't touch a grounded object. If your working hand accidentally touches something hot, you'll probably get a shock, but it won't go through your heart. Now, when you get shocked, current flows through you because your body is a conductor, just like his. The only difference is that your body has much more resistance. The amount varies from individual to individual and from moment to moment for any given person. In general, though, 30 volts is considered to be enough potential to push significant amounts of current through that body resistance. The severity of the shock depends on how much current is flowing through you. 1 milliamp or less is not even noticeable to most people. This current level, which is 1,000th of an amp, won't even give you a shock. Between 1 and 20 milliamps, you'll start to feel it. This can be a slightly painful jolt, and you'll notice some loss of muscular control. For example, you may not be able to let go of the source. 20 to 50 milliamps is definitely a painful shock. Muscle contractions become severe, and for that reason, breathing gets difficult. As currents increased to between 50 and 200 milliamps, the pain and contractions get worse. At somewhere around 100 milliamps, the heart goes into ventricular fibrillation, an uncoordinated vibration of the heart muscle that can result in death unless prompt medical treatment is given. At 200 milliamps and up, flesh burns. Muscle contractions are very severe. The chest muscles squeeze the heart, stopping it for the duration of the shock. This current level is only 1/5 of 1 amp. You'll be working on equipment that can carry hundreds and sometimes thousands of amps. The effects you've just seen depend on how much current actually flows through your body and on the particular path that it takes. Naturally, the more voltage there is, the more dangerous the shock hazard. The higher the voltage, the easier it is for it to overcome the resistance of your body. If you work on or around electrical equipment, you'd better know how to help victims of electrical shock. The first thing to do is cut the power. If you touch someone while they're being electrocuted, you'll get shocked too. If you can't cut the power, use an insulated pole or rope to move the conductor away from the victim or vice versa. When the victim has stopped breathing or his heart has stopped beating, you'll have to know how to revive him as well. A good training course in cardiopulmonary resuscitation is the best way to learn these techniques. Throughout this tape, we'll be looking at ways to recognize electrical hazards and prevent accidents involving electricity and other aspects of electrical maintenance. In this section, we've seen the effects of electrical shock, so when we return, we'll take a look at some safety devices, protective equipment that you can use to keep a shock from ever happening. When you're working on or near energized circuitry, you need special protection from electrical shock. Tools like these with insulated handles just aren't good enough. This type of coating is strictly for comfort. The plastic isn't rated for electrical resistance. So, when you're working around energized equipment, you need a better kind of insulation. These are all examples of approved protection from electrical shock. Gloves for low voltage and for high voltage. Rubber sleeves to cover your arms. Rubber blankets to cover up hot circuits before working nearby. And rubber floor mats to insulate you from ground. In this section, we're going to see how these items are all used, how they actually work to protect you from shock, and how they're inspected for safety. We'll start with gloves. These gloves are made of rubber with a separate leather cover to protect the material from punctures and other damage. The rubber is the insulating barrier. The leather is there to protect the rubber. When you're close to energized circuits, or circuits that may be energized, like when you're testing for hot conductors, gloves can prevent electrical shock by insulating your hands from the source. Here's an example. The electrical man has both hands connected source to source, but they're protected by the gloves. Now, let's turn on the power and see what happens. The gloves have insulated him from the current going through the cables. Our friend is not getting shocked. Your plant safety manual will tell you when you're required to wear gloves and what type of gloves to wear. We have two examples here. The gloves on the electrical man are rated at 600 volts, but these are rated to 20,000. If your hands are going to be near an exposed hot conductor, you have to have a glove rated for at least as much voltage as that conductor's carrying. And it's a good idea to have a safety margin as well. Now, rubber sleeves protect even more of your body. When they're used along with gloves, your hands and your arms are insulated from accidental contact with a source. Overhead work is one common application for sleeves. When you're working around several large high-voltage conductors, you need all the protection you can get. Up here, it's hard to keep your distance from the hot lines. Rubber blankets and floor mats are used in many situations. Blankets are used to cover up energized conductors when you have to work on something nearby. Floor mats keep you insulated from ground, so if you do contact something hot, the current can't flow through your body to ground. Here's a typical application for rubber blankets. Covering the energized main buses in a breaker panel before working on a de-energized breaker. Once the hot buses are covered, it's safer to reach into the breaker load terminals. Now, I'll show you how a floor mat works with the aid of my little green friend over here, our favorite shock victim. One hand is connected to source, and one foot's down here on this rubber mat. Of course, the opposite foot is touching ground. You ready, my friend? Here it comes. As you can see, current is flowing up the arm, through the heart, and down through the opposite side of the body. Contact with ground provides a complete path for electricity. So, if we insulate both feet, we should be able to prevent the shock. I'll move the mat over so both feet are standing on it. Now he's not touching ground at all. Let's put the switch back on. Now, here comes the power, and how about that? No current flows. You see, removing all contact with ground breaks the current path. So, even though he's touching an energized conductor right here, breaking the connection to ground keeps current from passing through his body. Now, all of the protective equipment we've been talking about is insulation. Gloves, sleeves, blankets, and floor mats insulate you from current sources or from ground. So before you use any of this gear, you have to make sure that the insulation is in good condition. Before you start a job, there are a few simple checks you can make. It's a good idea to inspect your gloves before each use. Check the rubber. Look for cracks, worn spots, cuts, and holes. To look for small punctures, you twirl the glove to inflate it, something like this. Then listen and feel for any leaks. If you find any holes or damage, turn in the gloves and get a new pair. Even a pinhole leak can make a difference. A small hole in a fingertip left a slightly larger hole in this man's elbow when it got near the grounded fuse box. That's why leather covers are important. The leather's there to prevent small cuts and punctures that can destroy the insulating properties of the glove. Sleeves, blankets, and mats are a little harder to inspect on the job. It's not easy to inflate these items, but what you can do is look at the rubber very closely. The best way is to roll the material tightly. You stretch the rubber. That makes it easier to spot any small punctures or cuts that might not show up with just a quick look. Of course, these on-the-job inspections aren't the only checks required for this kind of gear. Most companies have a periodic inspection procedure to thoroughly check the equipment every month or so. Here's a typical test rig for rubber gloves and sleeves. Gloves are hung in line on a rack and filled with water. Then the rack and the gloves are lowered into a tank that's also full of water. While the gloves are submerged, 20,000 volts are applied across the material. If the gloves are good, the voltage will hold. But if there's even a small leak, as you can see by the small glow inside the glove, the voltage drops far below the test value. Now these gloves will have to be tested individually to find out which one caused the indication. After all the gloves have been tested electrically, they're checked visually as well. This device inflates gloves so the technician can look for punctures or weak spots that might have escaped the electrical test. Even the smallest sound of escaping air means that the glove has failed. Sleeves are tested just like gloves. They're hung on the test rack, filled with water, and immersed in the tank. The apparatus is energized just as before, while the technician monitors the test voltage. Sleeves that pass the test are placed on another machine and inflated so they can be checked for cuts and weak spots that might fail in the future. Blankets and mats are tested on this device. The upper plate is connected to source, and the table is hooked to ground. For safety, the technician leaves the test cage before energizing the device. Then he passes 20,000 volts across the blanket, and if the voltage holds at 20,000, the blanket passes the test. On the job, your safety depends on the quality of your protective gear. If you use it right and treat it properly, you're doing yourself a favor. In sections to come, we'll be seeing just how some of this safety equipment is used for protection on the job. And we'll be looking at some of the general practices that can help you avoid electrical shock in typical maintenance situations. We've already seen how this equipment works and how it's inspected. So when we return, we'll be watching an actual maintenance job and see how all this gear is used safely. Much of the time, safety on an electrical job depends on knowing what's energized and what isn't. And of course, on the job, you have to depend on instruments to tell you. These are just a few of the different kinds of voltage detectors on the market. They aren't accurate measuring devices. All they're intended to do is tell you whether voltage is present or not. Since you'll be depending on them for your own safety, it's worthwhile to learn to use them correctly. The first thing to know is what detector to use. A low voltage device like this one might explode if you tried it on a 14 kV line. And a high voltage model won't necessarily give you any indication at all if you're trying to detect as little as 220 volts. I'm not going to give you any hard and fast rules here because there are a lot of different voltage detectors on the market. All I can say is find the approximate voltage range and use a detector that'll register in that range. The second important point is, how much do you trust these things? Well, you don't. Instead, you test the instrument before and after you check a circuit that's supposedly dead. You find something hot so you can make sure that your detector will register voltage. If there's nothing hot, you can check it on an approved test device. Then you check the de-energized circuit, and to make sure the device didn't die in between, you check it on a hot circuit again. That way, before you go sticking your hands into a bunch of wires, you can be pretty positive about what's hot and what isn't. Using voltage detectors properly is obviously pretty important to an electrical maintenance person, but it's hardly the only precaution you'll need on the job. To get an idea of some general safe practices, let's take a look at an actual maintenance job and see how we can turn a potentially dangerous operation into a safe one. A temporary feed's been hooked up to spare breaker 303 at this load center. The job is to remove the feed from the de-energized breaker load terminals. But since the rest of the load center handles essential equipment, the main bus will be hot. Before starting, the electrician checks the print and the tag to make sure he's on the right breaker. He can see that the breaker's open, but the tag lets everyone else know that it's to stay open until work's completed. For extra safety, though, he racks out the breaker before starting work. When the breaker's in this position, it can't be accidentally closed while he's working on the load terminals. Here on the other side of the load center, the work area's already been prepared with a barrier and a rubber floor mat. There'll be two people here, so one can help the other in case of trouble. There's a third person standing by the main bus breaker on the other side of the load center. He's ready to cut power to the main bus if there's an emergency. After getting his voltage tester ready, the electrician who's going to be doing the work puts on his gloves. He's already checked them right before coming on the job. Once they're on, he can start testing and find out what's hot and what isn't. First, he checks the main bus below the breaker load terminals. The bus is hot. Next, he checks the breaker load terminals where the temporary feed is attached. He checks line to ground and then across all three phases. Now he's sure that the load terminals are dead. That is, if the detector is still working. To make sure, he checks the main bus above the terminals. It registers hot, so he knows that the detector is working. And he knows that even though the main bus is hot, the breaker load terminals are de-energized. The next part of the job, then, is to cover the exposed main bus with rubber blankets. The bus bars run under, up the side, and over the terminals in question. So all three sides of the bus have to be covered with the blankets. Now it's almost impossible for the electrician's hands to come in contact with the hot bus bars. Before removing his gloves, though, he makes a last check to be sure that all the nearby bus bars are completely insulated. Then it's safe to take off his gloves and go to work. The wrench is tied to his wrist with a lanyard before he reaches in. That way, if he drops it, it can't bounce off the rubber and short out bus bars below.
Shorting the main bus would knock out a lot of equipment and make an arc that could burn or temporarily blind the electrician. In this case, it was safer to insulate the surrounding bus bars and then work without gloves. In this tight space, gloves would make the operation much clumsier. So as long as everything is de-energized or insulated with blankets, working barehanded is safer and faster. You'll notice, though, that nobody's wearing keys on their belt or has metal jewelry on. You shouldn't either, unless you're itching to play human lightning rod. We've been talking a lot about shock hazards and how to avoid getting shocked. I'd like to go back for a minute now and mention another type of electrical hazard: arcs. You saw how the electrician had the wrench tied around his wrist so he couldn't drop it and short out bus bars farther down in the cubicle. He didn't want to cause an arc that could burn or blind him. There are a lot of ways to cause arcs. For example, pulling out one end of an energized fuse. It's a much better idea to cut the power first, and then, just to make sure, pull each fuse with a sharp tug so both ends come out at once. If it's not possible to de-energize a box before pulling fuses, unload the fuse box. That is, turn off whatever's being powered by that line. If there's no current draw, you're much less likely to get an arc. In any case, though, make sure to use the right tool for the job. A fuse puller. They're insulated, so you can't get shocked even if the fuse breaks on you. And they keep your hands far enough away from the work to keep you from getting burned by an arc. Well, so far we've seen a lot of the kinds of precautions you need to take when you're working around energized equipment. But we all know that electrical maintenance is a lot more than just wiring. And in this type of work, electricity is not the only danger either. Take cleaning motors, for example. Many solvents used for cleaning release toxic vapors. You can get woozy enough to cause an accident, and even stand a chance of permanent damage unless there's adequate ventilation. Solvents used as aerosols or sprays are also dangerous in another way. The slightest spark can explode flammable solvent vapors in a confined area. Of course, it's best to use a non-flammable, non-toxic solvent. But in any case, make sure you have plenty of ventilation in your work area and wear the right kind of protective equipment. A face shield keeps the spray off your skin and out of your eyes. And even though a paper mask won't stop vapors, it will keep you from inhaling droplets of the spray. If you're in an area that can't be ventilated enough, you'll have to wear a different mask, one that chemically filters out vapors or supplies you with breathing air. Choosing the right solvent can help prevent these safety hazards, but there's another important consideration as well. Some solvents can damage insulation chemically, causing short circuits and even fires. Electrical fires can be pretty tricky, however they get started. What you don't want to do is act without thinking. Using a straight stream from a fire hose on energized equipment is a great way to get on the casualty list. You can use water, but only with special precautions. Here's what you should do instead for any electrical fire. First, cut the power. De-energizing the equipment removes the ignition source, so the fire will slow down. Second, report the fire. And third, use an extinguisher that's rated Class C for electrical fires. A type rated ABC will handle almost any kind of fire you're likely to run into. In your plant, you'll probably find one or both of these kinds of extinguishers: dry chemical or CO2. They're both effective on electrical fires if they're used correctly. CO2 is a little kinder to electrical circuitry because it doesn't leave any residue on the wiring, but CO2 also has another property that can directly affect your safety. When you start spraying one of these around, the gas inside displaces the air, In a confined area, CO2 can displace all of the oxygen in the room and leave you starving for air. At any rate, there's a lot more to fighting fires than you'll see here. It's a big enough topic for a specialized training course in itself. So let's stop here so you can review what you've learned so far about safety in electrical maintenance. Proper grounding is an important safety consideration on almost every kind of electrically operated equipment. On this electric motor, the ground bus electrically connects the housing to a grounding grid and to the earth. This ground connection is for safety. It's a pathway for stray current that might otherwise electrocute someone. If a motor like this one isn't properly grounded, a loose wire inside that contacts the housing will energize the housing and whoever happens to be touching it. But if the housing's grounded, a fault current will travel to ground, the path of least electrical resistance. People touching the housing aren't likely to get shocked. Of course, portable electric tools also have to be grounded, and hopefully, if there's a fault, the shortest path to ground won't be you. Electric tools with metal casings should be equipped with a three-pronged plug like this one. The third conductor connects the casing to a grounded terminal in the receptacle, so stray current to the housing travels to ground without going through your body. On the other hand, double insulated tools don't have to have a ground conductor. They have plastic casings that insulate you from any fault inside the tool. If the casing's in good condition, there's very little chance of getting shocked. Grounded tools with metal casings are much more common, though, so let's see how they're inspected for safety. The power cord is the place to start. Frayed or damaged cords are cause for many accidental shocks. If the cord looks okay visually, the next step is to check the drill electrically. This electrician's going to use a multimeter to check the continuity of the drill's ground conductor. He puts the selector switch on ohms and touches the probes together to zero the meter. Now he's ready to start the test. One probe goes on the plug's ground conductor and the other goes to the casing of the tool. The meter reads 0 ohms, so the tool's casing has a good conductor to ground. Now that he knows that the drill casing has a good ground, his next test is to see if there are any faults between the line conductors and the casing. He'll make a resistance measurement with a megohm meter. A low resistance reading between the ground conductor and a line conductor would indicate a fault. To make sure the test checks all the circuits in the drill, he locks the switch in the on position. The resistance is near infinity. No sign of a fault here. To double-check the test, though, he'll repeat it after switching a probe to the other line conductor. Resistance still reads infinity, so he knows that the first test was accurate, and neither line conductor is shorted to the casing of the tool. The last electrical test is to check the switch on the drill motor. He connects the probes line to line. With the switch on, he gets a fairly low resistance. With the switch off, he gets an infinite resistance again. That means that the switch cuts power completely when it's in the off position. All that remains is to give the drill an operational test. But first, let me introduce you to two pieces of safety equipment: a ground fault interrupter and a receptacle tester. A ground fault interrupter, or GFI, senses any current passing through the normally de-energized ground conductor and cuts power to the tool in a fraction of a second. If a GFI is plugged into a properly wired receptacle, any fault to the tool's casing will trip the unit almost before you can get shocked. The test button feeds a small current through the ground terminal so you can check the device, and the reset button restores power after the unit has tripped. A receptacle tester like this one tells you if a socket is properly grounded and whether it's wired with the correct polarity. If a socket's wired and grounded correctly, these two lights come on. As an added feature, this one also has a button for testing ground fault interrupters. So before testing the drill motor, he plugs in the GFI, tests it, and resets it. The receptacle tester indicates that the receptacle's properly wired and grounded, but he tests the GFI one more time just to be sure. Now he can go ahead and plug in the tool and test the action of the drill motor. Any fault to ground that went undetected before would trip the GFI almost as soon as he pulled the trigger. Portable ground fault interrupters are getting to be fairly common. They're about the best thing we've got for preventing shocks due to ground faults in electrical tools. But they're not foolproof. If a receptacle's not wired or grounded correctly, a GFI can't work the way it's supposed to. And that's where this comes in. Just by sticking it in the socket, like so, you can check the polarity and ground. And with this button, you can test a portable GFI, or even test a GFI that's permanently wired into the electrical system. In our last example, we saw a drill motor being tested for potential shock hazards. However, other tools and equipment that are part of an electrical maintenance person's job are potentially dangerous in other ways. For example, consider a soldering iron. Of course, we all know they get hot, so we try to remember to pick them up from the right end. But did you know that solder fumes are poisonous? Melting solder gives off lead vapors, and lack of ventilation can leave you a brain damage case, like this guy. Then there's always someone who flicks hot solder off his iron without looking. He's even dangerous to innocent bystanders. Here's a better way to go about it. Make sure your work area is well ventilated. Then, instead of flicking excess solder off the tip, wipe it on a damp sponge. A good stand like this one will also keep the hot iron away from flammable objects and within easy reach. Now, I'll admit that soldering isn't the most exciting job you could hope to see, but then no maintenance job is that exciting. That is until something goes wrong. Think of the possibilities right here in the battery room. Batteries like these give off hydrogen gas as a byproduct, and it just so happens that hydrogen gas is explosive when mixed with air. Unless you want this kind of excitement, don't smoke near batteries, and use only sparkless tools when working nearby. Batteries also contain acid, which is corrosive to skin and other nice things you might want to keep. Chemicals like this deserve a little bit of care in handling. Of course, there's also a shock hazard. Batteries this size generate enough juice to kill a man, so it's to your advantage to avoid carrying metal objects when you're working around them. That even includes rings, watches, and keys. The right way to work around batteries is carefully. The guys on this battery crew are a good example. They're wearing aprons, sleeves, gloves, and face shields. Acid's going to have a hard time getting to their skin or in their eyes. If it does, though, there's a wash station nearby. If they get any acid on them, they can flush it off with the liquid in the bottle. Before you work on a battery, find the nearest wash station and learn how to use it. If you get any battery acid on your skin or in your eyes, flush the area with lots and lots of water or with a neutralizing solution from a wash station. Then see your doctor. Chemical hazards often have a way of working on you without you even knowing it. Sometimes trouble doesn't show up until much later on. Battery acid isn't the only chemical hazard you'll run into when you're working with electrical equipment. You'll find some other potentially dangerous chemicals in other places. For example, in transformers. Large transformers like these generate a lot of heat when they're operating. So inside the can, there's a liquid that functions as both coolant and insulation.
Many transformers are cooled by chemicals called polychlorinated biphenyls, or PCBs for short. PCB is an environmental contaminant, and it's also suspected of being a cancer-causing agent. Unfortunately, that isn't all. When PCB gets hot, like when a transformer's operating, it releases a poisonous gas called phosgene. If you have to open a transformer for maintenance, give it plenty of time to cool off before opening it up. PCB is also used in large capacitors. Whenever you see labels like this, you know that you have to be extremely careful about handling the stuff inside. Storage, handling, and disposal of PCB is regulated by law in the United States. Spills have to be reported to the appropriate federal agency, and PCB from used transformers and capacitors has to be stored in leak-proof containers until proper disposal can be arranged. If there's a chance of getting PCB on your skin when you're working, you'll need the right kind of protective equipment. A complete rain suit with boots, gloves, and eye protection is the best way to keep from being exposed. You want to keep PCB off your clothes, too, because you don't want to be tracking it home to your family. Now, not all transformers are filled with PCB. Most are cooled with mineral oil, which is flammable, but not nearly the same kind of contaminant. The problem is that often you don't really know what's inside a transformer until it's been tested. It's been discovered that many oil-filled transformers also contain small amounts of PCB. So until you have real laboratory evidence, you have to assume that any transformer contains at least some PCB and use the same kinds of precautions you would if you were handling the raw chemical. Well, we've come a long way from electric drills in this section. We've seen the safety aspects of grounding, soldering, battery maintenance, and finally, handling PCB. These are just a few of the not-so-obvious hazards in electrical work. In the next section, we're going to take a look at some common electrical components and devices and see some more hazards that aren't always noticed at first glance. Before we go on, though, take some time to review what you've learned about electrical tools and special equipment hazards. In this section, we're going to be looking at some components and devices that present special hazards to electrical maintenance workers. The first group of components we'll talk about is capacitors. Capacitors are components that store a charge. You'll find them in motor starters, communications equipment, and in many other applications. As you can see, they come in many shapes and sizes, but they all work basically the same way. Inside a capacitor are two plates separated by an insulating material called the dielectric. If you apply a voltage across the plates, the capacitor begins to charge up. One plate takes on a positive charge and the other is charged negatively. If you remove the power source, the plates remain charged. The capacitor stores the charge. If you connect the two wires leading to the plates, the capacitor discharges. It releases its charge. Let's see what this looks like in actual practice. This capacitor's already been charged. We're going to measure that charge with a multimeter. A probe goes to each capacitor terminal. It's kind of hard to see here, but the meter reads 430 volts. Now we're going to see the capacitor discharged safely through a resistor. This 10,000 ohm resistor will slow down the discharge, so we can see it happen gradually on the meter. Once the resistor is connected across the terminals, the voltage slowly drops. The capacitor will continue to discharge until it's down to nothing. The only safe way to discharge a capacitor is to short it with a resistor of at least 1,000 ohms. Slowing down the discharge reduces the hazard. Let's see why. We're going to discharge this one all at once. As you can see, the screwdriver is slightly the worse for wear. The consequences are obvious. Even if a piece of equipment is unplugged and de-energized, capacitors can store enough charge to give you a good jolt unless you discharge them properly. A large capacitor bank can be even more dangerous. Hundreds of thousands of volts could be released here, so it's extremely important that they're discharged and grounded before any maintenance takes place. The first step is to de-energize the bank. This open disconnect switch means that the power's been cut. Now, internal resistors built into the capacitors will slowly discharge the bank for a period of at least 5 minutes, the minimum time for safe discharging. During the wait, the electrician checks his voltage detector on an energized source. This type, called a glow tester, has a circular neon tube that glows when it comes near an alternating current source. Once the required 5-minute wait is over, he can open the gate leading to the capacitors. At this facility, a key interlock system controls access to the area. It can't be unlocked unless the capacitor bank disconnect switch is open. To make sure that the bank is de-energized, he checks it with the glow tester. It shows no indication, which means that there's no AC going to the frame. It doesn't mean that the capacitors are completely discharged. Just to be certain that his detector is still working properly, he tests it again on a source that's known to be energized. The next step is to ground the frame of the capacitor bank. Using an insulated pole called a hot stick, he closes the ground switch. In this case, the frame of the capacitor bank is one of its main terminals. Now that the frame is grounded, he can short out each row of capacitors one at a time. Shorting the capacitors to the frame means that any remaining voltage discharges to the frame and from there into the ground. Smaller capacitors should be treated the same way. De-energize the equipment, discharge through a resistor, ground one terminal, and then short the terminals. That's the safe procedure, no matter what size the capacitor. Proper discharging, grounding, and shorting are essential to safety whenever you're working on circuits that include capacitors. However, with some capacitors, there are other hazards just as important. These are all electrolytic capacitors. We give them that name because they're filled with an electrolyte, a corrosive chemical paste. You can recognize electrolytic types because they're all marked for polarity. On this one, a red dot indicates the positive terminal. And on these, there's a plus marked on the positive end. The reason that these are marked for polarity and other capacitors aren't is that electrolytic capacitors are polarity sensitive. If they're hooked up backwards, they'll explode. Let's see what that explosion looks like in the laboratory. This electrolytic capacitor is hooked up to a DC power source, but it's hooked up backwards. Let's turn the power up and see what happens. If you were standing there without protection, you'd have caustic electrolyte on your face. It's not likely to be your favorite kind of makeup. The capacitor you just saw used to be one of these, a little 50-volt capacitor. Now, try and imagine one of these blowing, kind of like a grenade. It'd make quite a bigger bang for sure. That's why we didn't try it, even in the lab. There are a few other devices at any large plant that'll surprise you as well. As an electrician, you know something about meters, right? But have you ever thought about how you'd take a reading on a 14 kV line? On high voltage, high current lines, you just can't go around with a multimeter and directly measure everything you need to know. On equipment like this, there are built-in transformers that reduce the current or voltage to levels that meters can handle. Current transformers feed ammeters, and potential transformers supply the voltmeters. If you ever have to test or replace meters like these, you'd better learn the difference. For example, say you had to test an ammeter. Would you just unhook the meter and plug in a portable? If you did, you'd have a surprise coming to you. When you break the secondary of a current transformer, voltage zooms up, enough voltage to weld with. To be safe, you have to short the secondary instead. Then it's okay to disconnect the panel meter and plug in a portable. It's better to de-energize everything first, but if you can't, remember, never open the secondary of a current transformer. A lot of meter panels have special test terminals that make this whole process unnecessary. With the right kind of probe, you don't have to open the circuit at all. This probe has two conductors that are separated by an insulator over their entire length. These test terminals are made of springy metal. Normally, their spring tension holds them tightly together and keeps the circuit closed. But when you insert the probe between the terminals spread apart. The circuit is never open, and the portable meter is safely connected in line. As far as current transformers are concerned, that's the real safety point to remember. Don't open the secondary. If you have to remove an ammeter, de-energize the line or short the secondary so it's never opened. Taking voltage readings is a different story. You never have to open a circuit. All you have to do is measure each phase parallel to ground, or measure phase to phase. There's another difference too. When you're removing a voltmeter from a potential transformer, you don't short the secondary. That'll create enough current to blow up the transformer and everything connected to it, which you might not notice when you're knocked unconscious by the shock. If you have to replace a voltmeter or work on a panel that's fed by a potential transformer, you open the transformer primary instead. That way you can avoid accidental shorts and the high current shocks they cause. By this point, many of you have probably found out that there are a lot of things about electricity and electrical safety that you hadn't thought about before. Well, I've got a few more surprises for you, too. But first, why don't you review what you just seen and get ready for some high voltage hazards. When you see a sign like this one, it's pretty obvious that you'll be safer if you keep your distance. To a high voltage line, your body presents practically no resistance. An unprotected person doesn't stand a chance if he grabs a few thousand volts in one hand and touches ground. Yet working on or near high voltage conductors can be safe with the right protective equipment and the right techniques. It's a matter of knowing exactly what the hazards are and how to protect yourself from them. In this section, you'll see some of the techniques and precautions used for working on high voltage equipment and learn about some of the not so obvious hazards that high voltage can present. Let's start with an experiment using a high voltage coil. The coil's de-energized right now, no current is flowing. Several feet away, there's a person holding an ordinary fluorescent tube. The tube's disconnected. No wires are attached. Watch what happens when we energize the coil. The high voltage circulating in the coil induces current and voltage in the fluorescent tube. Even though the tube's not connected to the source, it's close enough to be charged up by the electrical field around the coil. Now, watch what happens when we de-energize the coil. The tube is still glowing. The capacitance of the fluorescent tube causes it to store a charge. It'll glow for a while and then slowly fade as it discharges. What you've just seen is an example of induction and capacitance. The electrical field surrounding the high voltage source induced a charge in the fluorescent tube, and the capacitance of the tube stored the charge. This has direct consequences for high voltage electrical maintenance. Here's an example. Two high voltage transmission lines run side by side. One's energized and one isn't. The energized line is surrounded by an electrical field, and since the field intercepts the de-energized line, it induces a voltage there. Due to capacitive effects, the charge continues to build up. The voltage in the de-energized line can be as high as that in the energized line nearby. To make the de-energized line safe to work on, the induced charge has to be drained off by grounding the line. The grounds discharge the induced voltage into the earth. If a line's not grounded properly, it can store up thousands of volts, even if it's not connected to any power source. Many types of high voltage equipment are designed with special arrangements for safety grounding. We're going to see two different examples of isolating and grounding equipment for maintenance. This transformer is our first example. An electrician's going to prepare for work on the 230 kV primary side of the unit. The transformer has to be unloaded on the secondary side and de-energized on the primary side. Then the primary has to be grounded. On this job, the process starts with calling the dispatcher to get clearance for the work. The dispatcher is responsible for rerouting the load and performing the initial switching. In this case, a transformer primary has to be isolated from a 230 kV line. By remote control, the dispatcher unloads the transformer by opening the secondary breaker. Then he cuts power to the transformer by opening the primary breaker. He also isolates the primary by actuating a motor-operated disconnect switch on the incoming line. It's up to the electrician to lock the motor-operated switch in the open position and tag it out so the transformer primary won't accidentally be energized. His next move is to isolate the secondary. This disconnect is manually operated. Opening the secondary side of the transformer ensures that voltage from interconnected equipment downstream can't feed back into the transformer. Now the transformer is electrically isolated on both sides. This switch is also locked and tagged so it can't be closed accidentally. Before starting work on the primary, he has one last precaution to take. He has to ground the primary. The ground's closed by this manually operated switch. Turning the crank closes the grounds on all three phases. Once they're closed, any induced voltage on the primary is discharged into the earth. If he had to work on the secondary side as well, he'd have to attach portable grounds over there. To make sure the primary stays grounded, he locks the switch in the closed position and tags it out so the ground won't be opened while he's working on the transformer. Here's what the situation looks like now. Open breakers and disconnects isolate the unit on both the primary and secondary sides. In addition, the primary is grounded. After making routine checks for voltage, he can work on the primary without risking a shock from induced voltage. Proper switching and grounding are the real keys to making maintenance of high voltage equipment as safe as possible. We've seen one example, but many installations use other methods on 4 kV and 14 kV equipment. A common technique is to ground a line, a transformer, or a bus with a ground test device that racks into a breaker panel.
First, the line's unloaded and de-energized, typically by the dispatcher. The next step is to rack out the breaker so it's no longer in the circuit and roll it out of the way. This is the ground test device. It's kept in its own storage cubicle when not in use. The purpose of a ground test device is to ground equipment for maintenance or to synchronize phases when you're putting equipment back online. It rolls right into a breaker panel and racks into position the same way a breaker does. On this type of switchgear, a small electric motor is used to rack units in or out of contact. Actuating the motor raises the unit into position. For his own safety, the electrician stands to the side while he racks in the device. Now the unit's fully racked into position, but the ground isn't closed yet. Before closing the ground, he tests all 3 line terminals for voltage. If the line was energized, grounding it could be an explosive experience. For extra safety, the switch that operates the device is mounted on a 50-foot cord. After it's connected, the electrician places the selector knob in the line ground position and steps back. Now the line is safely grounded. Well, now you've seen 2 typical examples of switching and grounding high voltage equipment. You also saw why proper grounding is important. Induction and capacitance can create a high voltage charge even on equipment that's been de-energized and isolated. There's a lot more to electrical maintenance than you've seen here, but you have seen the essentials of safety, good work practices, and correct use of protective equipment. Another big part of safety is recognizing the hazards, being familiar enough with the equipment to know what's likely to bite and what isn't. In this unit, you've seen a number of examples, but a lot of this knowledge has to come from experience. If you go about gaining your experience with a certain amount of respect for electricity and what it can do, you've made a pretty good start toward being a safe electrician.